In 1859, telegraph lines caught fire by themselves without anyone touching them. And if that happened today, the internet shuts down. Banks stop working. Hospitals lose power, not in days, in hours. The thing that can do this, it's not a bomb, it's not a hacker, it's not a war. It's the object you look at every morning without thinking about it. And the part that really bothers me, we still can't predict it. In this video, you're going to discover 3 things. 1. Why the sun breaks the laws of physics. 2. How it forced scientists to admit their best theory was wrong. 3. Why we are still completely at its mercy. Let's start with the event that changed everything. September 1st, 1859. Astronomer Richard Carrington is observing the sun, and suddenly, a blinding flash erupts across its surface. It lasts a few minutes, then disappears. Carrington writes down the exact time. 17 hours later, Earth gets hit directly. Telegraph lines throw sparks, operators receive electric shocks. Auroras appear above Central America. Communication lines catch fire. And back in 1859, humanity barely even used electricity. Today, scientists estimate that the same event would cause between $600 billion and $2.7 trillion in damage. Satellites, GPS, banking systems, internet, hospitals, potentially gone within hours. And the worst part? We couldn't predict it in 1859. We still can't accurately predict it today. But before we get to the real threat, I need to show you something even stranger. Because the sun does something that physics says should be impossible. Here's a rule your body understands instinctively. You move farther away from a fire, you get colder. Makes sense. Now apply that to the sun. The surface of the sun, 5,500 degrees. The atmosphere above that surface, over 1 million degrees. That's like walking away from a campfire and instantly becoming 180 times hotter. Physics says that shouldn't be possible. The sun does it anyway. Scientists discovered this in the 1940s. It's now 2026. We still don't know exactly why. 2 theories are fighting for the answer. Alpha waves, giant magnetic waves carrying energy upward. Nanoflares, millions of tiny invisible explosions happening constantly. NASA's Parker Solar Probe recently flew within 10 million kilometers of the sun, closer than any human-made object in history. It confirmed that both phenomena exist. It still didn't solve the mystery. We are sending machines into the atmosphere of a star, and we still don't understand why that atmosphere is hotter than the star itself. But as bizarre as that paradox is, it is not the discovery that truly terrified physicists. Because when scientists tried looking inside the sun, they found something missing. Here's the problem with the sun. The light we see today actually began its journey from the sun's core somewhere between 10,000 and 170,000 years ago. Energy takes thousands of years to reach the surface, so we cannot see inside the sun using light. Scientists needed another method. The sun vibrates like a gigantic cosmic bell. Its entire surface ripples constantly. By analyzing those vibrations, a technique called helioseismology, physicists can map the sun's interior, exactly like geologists use earthquakes to study Earth's core. And while studying that core, they discovered something was wrong. In the 1960s, researchers built giant underground detectors. Their mission: capture neutrinos, ghost particles created inside the sun, so elusive that they can pass through an entire planet with almost no interaction. The detectors worked, but there was a problem. They detected only 1/3 of the expected neutrinos. 1/3. 2/3 had vanished. Physicists faced a terrifying choice. Either we completely misunderstood how the sun works, or modern physics itself was incomplete. For 40 years, nobody could solve it. The mystery became known as the Solar Neutrino Problem, and for 4 decades, it haunted particle physics. Then, in the early 2000s, the answer finally arrived. The neutrinos had not disappeared. They had transformed. They changed identity while traveling through space. Our detectors could only see one type. The other 2 passed straight through unnoticed. And this discovery changed physics forever. Because for a neutrino to transform, it must have mass. And according to the standard model of particle physics, the most tested and accurate scientific theory in history, neutrinos were not supposed to have mass. The sun had forced physicists to admit something horrifying. Their best theory was incomplete. That discovery earned the Nobel Prize in 2015, and it revealed something much more unsettling about our understanding of the universe. Here's what really bothers me, not in an abstract scientific way, in a practical way. In 1989, a solar storm far weaker than the Carrington Event collapsed the entire power grid of Quebec. 6 million people lost electricity. For 9 hours, transformers overloaded, some melted from the inside. and that was considered a relatively minor event. A true Carrington-level storm today could damage transformers across entire continents. Some of those transformers take months to replace, sometimes years, and we still cannot precisely predict when a major eruption will happen. We know they become more common during solar maximum, but we cannot say, in 48 hours, this exact region of the sun will explode. The sun's magnetic field is chaotic, violently chaotic. The instabilities that trigger eruptions happen too fast and too randomly to model in real time. Our warning systems can give us hours, not weeks. Humanity is trying to protect a civilization worth trillions of dollars using forecasts that are still partly educated guesses. And there's something else, a question scientists still cannot fully answer, even though we've been observing it since the 1600s. Sunspots follow an approximately 11-year cycle. At peak activity, the sun becomes covered in dark magnetic regions. At minimum activity, it appears almost smooth. We have documented this cycle for centuries, and we still do not fully understand why it lasts 11 years. In the early 2010s, solar cycle 24 became unusually weak. Some researchers feared the arrival of a new Maunder minimum, a historical period where sunspots nearly disappeared for decades. Coinciding with part of the Little Ice Age, people started asking, could the sun cool the Earth? Then solar cycle 25 arrived, much stronger than expected. Our models were wrong again. So here are the 3 answers I promised you. 1. Why the sun breaks the laws of physics. Because its atmosphere is 1,000,000 degrees hotter than its surface, and we still do not fully understand why. 2. How it forced scientists to admit their best theory was wrong. The neutrino problem proved that the standard model is incomplete, which earned a Nobel Prize. 3. Why we are still at its mercy. Because a storm like the one in 1859 could shut down electricity and internet across entire continents, and we still cannot predict it accurately. But what fascinates me most is not that the sun is mysterious. It's that the most studied star in the universe, the one we see every single day, still contains enough unknowns to shake modern physics. Why is the corona so hot? Why does the cycle last 11 years? Still debated. How do we predict eruptions? We're not there yet. Parker's solar probe continues diving deeper into the sun's atmosphere. Solar Orbiter captures the first detailed images of its poles. The data keeps coming. Maybe one day we'll understand these mysteries. But today, no. And if the closest star to us can still surprise us this much, what does that say about the billions of stars we observe light years away? Stars we will never touch. Stars we may completely misunderstand. In the next video, we tackle one of astronomy's biggest assumptions. What if part of what we think we know about distant stars is wrong? If this video surprised you, tell me in the comments. Which mystery shocked you the most? The impossible heat of the corona? The neutrinos that broke physics? Or the fact that the sun could potentially shut down our civilization tomorrow morning?